It is, yeah.
Isn't this kind of like, so when you find the Lyapunov function, you're trying to find a cost function for the dynamics?
Well,
that's an equilibrium point?
Well,
like inversely a bit?
Well, that's going to be, have you read the notes?
No, just look from the picture of the day, because you see the same picture in a constrained optimization text.
Yeah, right.
You're traveling on with dynamics.
Oh, I see.
Which are like your constraints and the Lyapunov function. You go in the negative direction of that.
Right.
Stay along that path.
Yeah, well, I don't know, because there's nothing about trying to stay on a path here. I mean, we've got a constraint here.
Well, the dynamics are the path.
Yeah, that's the path. And so there's nothing about trying to keep it. There's no control, there's no input here, so.
But isn't that implicitly what's happening? Not implicitly what's happening.
No, we've closed the loop here, and now we're trying to evaluate our closed loop behavior. Yeah, so I don't know. It's hard to, your question's too abstract for me.
Okay,
Yeah.
I'll have to formalize it.
Well, think about it, because we have another minute, but yeah.
So all this is saying, right? It's like the state eventually will converge to an equilibrium.
I mean, that's what it's saying.
Like it won't wander around forever.
Yeah. That's right. I guess we can get started?
Yeah.
Are we on? Yeah, it's time. Yeah, so basically, so last time I was basically reviewing this basic dynamical systems theory, state space theory. We have a dynamical system, which you can think of as what happens after we close the loop. So this was a controlled system like a robot or something. And this is the closed loop behavior. Typically that's the situation. And there was some equilibrium behavior we desired, which is, say, an airplane being at level flight, 30,000 feet above the sea level. So X star is position and orientation and velocity and all of that. Hey, Niran, you were volunteered to help with videotaping sometimes. And so the way to check to see if you actually reach and stay at that equilibrium is to find a function v, which is called a Lyapunov function, that's decreasing. So v is non-negative, and it's decreasing as time goes on. And if you can find a function satisfying this, so v of xt is decreasing whenever xt is not at the equilibrium. And by the chain rule, that's equivalent to this. So you just go through and take the derivative with respect to v, and then derivative of x with respect to time. The derivative of x with respect to time is f of x. So you get that from the chain rule. And I gave geometry last time, and realized this morning that I never gave you the punchline, which is that if you have one of these equivalent properties holding, then x of t does go to x star as t goes to infinity, and a bit more. So there's sort of this local continuity that if I start near x star, I stay near x star, which I'm not going to talk about. So take a nonlinear control course and you'll learn about that. And that's global asymptotic stability. That's what it's called. All right? All right. So I'd say a little bit more in the notes. So if you look, so you've all hopefully downloaded those notes and are reviewing them. In this course, we're more interested in performance bounds and things like that. We're going to be given a cost function. In this case, we're in RD. Yeah. And we're not just going to ask for this equation to hold. We're going to ask for a decrease at least of the amount minus c. Now, this inequality and this inequality are sort of the same, because I can always define this to be c of x, right? I could always say my cost function is this dot product, minus this dot product, all right? And that'll be some positive function, and it'll be positive everywhere except for at x star. And in fact, in order for this to even make sense, we're going to need c of x star equals 0. For any of this to make sense. And then you can go through and do some things that I've already done a few times. You can go back, reinterpret this as this, and fool around. So note, this thing that I'm writing down here is the same as saying that the derivative with respect to time of v of xt is less than or equal to minus c of xt. Right. And then you can use a bit of calculus. You can basically, I'm going to integrate both sides with respect to time. So you all remember your fundamental theorem of calculus. I think I asked you to review that. The difference of the endpoints is the integral of the derivative. Okay, and that derivative again is bounded by minus c of x of t, and then you can go and move things around, and also you might as well do this. All right, so I assume that my Lyapunov functions are always non-negative. All right, so I can throw this away and just replace it by this. And so you move terms around. So I take this to the right-hand side and this to the left-hand side, and I get a bound. So you get this total cost bound. And of course, if this is true for every t, then I can let t go to infinity, and that's what people typically want. That's it. So this slightly stronger Lyapunov drift condition, it's called a Lyapunov drift condition. That's what it's often called. It's a drift downwards. Implies it's performance bound. Okay. And so, this is just how nonlinear optimal control is presented. You're told this is the objective we'd like to, say, minimize, and we'd like to get bounds on this cost as a function of, basically choose a policy, say, to make this total cost as small as possible. That's all of nonlinear deterministic optimal control is based on this total cost criterion very often. I mean, not always going to infinity. Sometimes you have finite horizon problems, but infinite horizon is simple in a way. I mean, it is. All right. So anyway, this is one thing I want to generalize to Markov models, and it turns out for Markov models, it's actually even, I would say, even simpler than deterministic. And it's just nice to be able to see it for the deterministic case first, because a lot of you are maybe scared of stochastic processes and all the Markov notation, but you're not scared of calculus. I mean, the fundamental theorem of calculus, you might have forgotten it. Well, I'm sure it's back in your brain now. Okay, that's why I do this deterministic case first. So this is perfectly generalized to the stochastic case, except for the fact that total cost easily makes no sense. Usually this thing is bubbling around. There's no way this goes to 0 in many cases, and so you have to come up with different objectives. Okay. The next thing in the notes is about converse theorems. So this goes one direction. If I can find a Lyapunov function, then I have global asymptotic stability. You know, and it turns out there's a very precise converse. You know, so basically, there's always a Lyapunov function subject to something, and the form of the converse theorem is obvious in a way, because if I had put an equality here, then I'd have an equality here, and I'd have an equality here, and so forth, and everything would be equalities. So the Lyapunov function would be equal to this, what's called a value function. And so that's it. All right. So suppose this system suppose somebody, not only do we have global asymptotic stability, but it goes to zero fast enough so we have, with some cost function, we get a finite total cost. That's always going to happen. I mean, all right, so this is what I'm saying. If you go through these steps, you can see, well, that this function, the initial condition, should be the Lyapunov function. And yes, it's trivial to see that's true. And I'll explain that. So this will be a solution to this with equality. And I have to be a bit careful. Okay, so I've got this identity holding for all t, and I mean necessarily. Can you all say why extra? This has to be true. Can somebody tell me why this must be true? I'd have to assume it. Well, J is finite valued, right? And x star is an equilibrium. If I start at x star, I stay there forever. So if I plug in x star here, then xt is x star for all time. So for this to be finite valued, c of x star has to be 0. So that's just it's a consequence of the assumptions. So anyway, so I'm going to show you this, and then I have to say, well, then if J is continuously differentiable, then I can apply the chain rule. You know, so unfortunately, that's unfortunate. I mean, how on earth are you going to check that J is smooth? But anyway. Okay, cool. But at least we always have this, you know. And so you can imagine it's probably pretty generic that F is is smooth in some sense. And do you all know how to prove 1?
Isn't it just the interval?
Exactly. I mean, it's just, well, I mean, it's not 1 line, but it's 2 lines. It's Bellman again. You know, the total cost is the cost up to time t plus the cost to go. So it's Bellman. So I only have to prove 1 because this is a chain rule, you know. So actually, I want to use different notation. That's right. Yep. So I hope that's obvious to you, and if it's not, think it over, because this is really important. You know, this Bellman equation is going to come up throughout the course. Every single week, we're going to have things like this, you know. So if it's not clear, think it over and then come and talk to me. But you have got the total integral is the integral from 0 to t plus the integral from t to infinity. And that's the total cost from wherever I ended up, you know, at time t, you know. And now you take 2 values. You set t equals t plus delta and t equals t. And why do you do this? Because I'm trying to prove something about derivatives, and so we all know about what a derivative is. I've got a, you know, we have to go back to the definition of derivative. So let's use a different pen or something. I've got j of x0 equals the integral from 0 to t plus delta with a little t. So you can see why I use c of xr dr, because I've already got a t sitting there. I'm preserving my t's. And so I've got, you know, the total cost starting from x0 can be written in 2 different ways. And I'm going to take differences. All right? And so this minus this is 0. This red is annoying. You know, the integral from t plus delta minus the integral from 0 to t is just the integral from t to t plus delta. I better say it's continuous. I didn't do that, did I? Forgot to say that. Assume c is continuous, so we'll be screwed right here. And I forgot to say that in my notes as well. C has to be continuous, I think. Maybe not. Maybe it's in the notes. So I take the difference, and the difference, this minus this is just the integral from t to t plus delta. And there's a 0 there, so I can divide both sides by delta. And so I'm just reciting my notes to you. So you can find all of this in the notes. All right. And so you can see why I suddenly panicked and said, oh my God, C better be continuous. All right, because I know xr is a continuous function of r because it satisfies a differential equation, and I want the c of xr to be a continuous function of r as well. And so then if I let delta go to 0, I'm just going to get, you know, c of xt. All right, and when I let delta go to 0 over here, I just get that. All right, and that's it, QED. a black box or QED means proof is over. All right, proof is over. I'm just saying let delta go to 0. When delta goes to 0, this is C of xt, and that's the derivative of j. All right, cool. Okay, so anything else? Any questions? Okay, I'm going to blast through one more drift condition, and then we'll go to Markov. I can kill this, right?
I have a quick question.
Yeah.
So we did this proof with no control input, and later
Yeah.
generalize it to
Yeah. Yeah, that's right.
that.
Yeah. I mean, so again, you know, in the course, sadly, I'm going to this linear thing. I'm looking at really understanding Markovian models without control. And for that, I'm following like a deterministic optimal control course where you'd first understand dynamical systems, you know. And then I'm going to introduce the control, and these dynamic programming equations to synthesize optimal policies are just little generalizations of these things, you know. And so that's why it's useful pedagogically to have that foundation before you get to the optimal control. It sucks from the point of view of fun, and that's why I really like to somehow have you play around with optimization before we do the theory. So yeah, so all this stuff is going to be generalized. I mean, we'll embed control as we go along. Now, the final, before we go back to Markov again, the final question is, what if there's no x star? You know, I mean, just think about x of t being some periodic orbit or something. You know, it starts off, maybe it cycles in, and it you know, it's just converges to some periodic orbit. So what's done in dynamical systems is the notion of ultimate boundedness. So this, you know, again, it's x dot equals f of x. So this dynamical system x dot equals f of x is called ultimately bounded if there exists some, say, integer m. I don't know why I say integer, but if okay. So instead of going, like, before we were converging to a point, and now we're converging to a ball. That's the way to think about it. You know, we've got x1 and x2, and we've got this ball of radius m. You know, and from any initial condition x0, we do all sorts of funky things, but eventually we hit this ball. Maybe we leave it, but then eventually we come into it and we stay in it forever. Yeah. Because that's what it's saying. Because the t is going to depend on x0. You know, if you're way out there, very likely it's going to take a long time to reach this ball and stay there. All right. And we have a drift condition for that. And I'm not going to get into all of it because this gets a bit subtle and tricky. But at least I can give you, you know, the main ideas. I'm going to give you the ideas that fit the Markov setting the best. Okay. And what we do is, it's gone now. Well, here's the Lyapunov criterion. We have the same grad v of x dotted with f of x is negative, but I'll make it precise. I'll quantify it. So I've got some minus c of x here, And I'll say some things about that in a moment. But then I relax this by adding a constant. And I'm going to call it eta bar, and the bar will be explained as we go along, because it gives you a bound. All right? And without even thinking, we can say a few things from this. So if C is coercive, so I wrote this down before. So C of x gets larger and larger as x, it doesn't have to be monotone, but C of x goes to infinity as the norm of x goes to infinity. I can give you a crisp mathematical definition of that if you like. And again, let's assume it's continuous. It doesn't have to be, but we might as well assume it's continuous. So for those mathematically inclined, this is equivalent to saying that the set Sn equals a set of x such that C of x is less than or equal to n. This set, it's called a sublevel set, is compact for each n, or bounded, say, for each n. It's a bounded set. Yeah. So these turn out to be equivalent. I know they don't look at it right off the bat, but they are. Just think about a graph. Coercive means, again, it doesn't have to be monotone, but it gets big for large x. What we're doing here, when we look at Sn, is we're taking a level n, and we're going downwards. And we're looking at the set of x for which C of x is less than or equal to n. That's a bounded set. It's the same as saying it blows up. So anyway, if it's coercive, then this condition implies ultimate boundedness. All right, and the proof of this is really involved, at least the proof I know. I'm not going to prove it. Okay, I'm going to prove something similar in the stochastic case, but I'm not going to do that. I will prove something trivial, and what will that be? Anybody can conjecture, anybody who hasn't read the notes can conjecture a performance bound? Gosh, it's awful. Anybody? Let's stare at this. Remember what this means. Let's write it down to make it easier. So what am I going to do with this? And it's going to repeat fundamental theorem of calculus, fundamental theorem of calculus. Right? And so if I integrate this from 0 to t, as we've all seen, you get v, I'm hearing you, great. And then I integrate this. And I get the cost over time horizon t. And then here I'm integrating a constant over a time horizon t, so I just get eta bar times t. All right. And again, just as before, that's greater than or equal to minus v of x0. Because we're just throwing this away because we know so little about it. This we know about it. We constructed V. We know our initial condition, and that's important. But we don't know. I mean, the thing we're trying to say something about the future we haven't seen yet. And then what you end up doing is you divide by t. You know. And so you get a really, really pretty bound. So you look how trivial this is. Just in a, just fundamental theorem of calculus, and we get a really nice bound. We get that the average cost, which is this, is less, I'm putting this to the left-hand side, is less than or equal to this Lyapunov function over t plus this bound eta bar. And there's the reason for the bar. So it's really nice, and basically tells you the average cost has a component due to the initial condition, and that decays like 1 over t. And then there's a bound on the long run average. Is that clear? So this is really in line with what you look at in Markov models. Typical, this average cost is a very common metric of performance, and we'll find that this exact same formula holds. We have to stick an expectation here, and we're going to get 1 over t times the Lyapunov function, and we're going to get a bound here. It's just that we have to translate this inequality to a stochastic setting. And we need a fundamental theorem of calculus, sort of, which we're going to sort of use without saying in discrete time for Markov models. All right. So this part of the course, I mean, basically you can see how simple this part of stability theory for dynamical systems is. And what I want to impress upon you is that the Markov case is even simpler. You get the same sorts of conclusions, and the arguments are identical. All right. Okay, it's really cute. So when you get to the finer thing, it's like you want to find, like you want to compute what this is, the minimal value. Then things get kind of tricky. I mean, impossible for deterministic systems, tricky for stochastic. But when you want to get these bounds and get these qualitative insights, it's like it's so elegant and simple, and that's really useful when we get to control and approximate dynamic programming and reinforcement learning. The fact that it's so easy. Okay. So should we walk away from deterministic systems for a while? I think I'm going to do the same thing when we get to optimal control. I'm going to go through the HJB equations more slowly. I did it way too fast last week. And again, try to impress upon how simple they are, and actually show there's a link between stochastic and deterministic models. It all depends on timing and all that. All right. You all look awake. That's great. So I can kill this. All right. Except that. And that. Okay. So this is the first thing I want to do. For Markov models, I want to write down an analog of that. All right. And that is equivalent to that. And so we're talking about derivatives in continuous time. For Markov models, we look at differences. That's the only difference. You had a question, or just gossiping?
So from a very big picture point of view, whatever we've been looking at, like the whole of Lyapunov theory as well.
Yeah.
So we were able to get a bound on the cost. And stuff. Like, where are we going with that?
Well, I want to generalize this to the stochastic setting. Yeah, I want to illustrate how simple it is in the deterministic setting, and I want to argue. Once you absorb the notation, it's just as easy in the discrete time Markov setting. It's all about what I was yelling at you all on Thursday, that if you don't observe the notation, you lost. I mean, you will not do well in the course. You won't understand a thing. So that's why, I'm really going to push you to, just internalize the notation. So, and in fact, I'm going to put it down right now. So for Markov chain, that word kernel strange, but I'll review what that means in a second. I'll do it right now. That just means that if I look at the probability that xt plus 1 is in some set S given xt equals x, that's equal to the probability from x to a. I mean S. And again, I'm avoiding like measure theory and stuff like that for a while. I think I might give you a tutorial in a bit, but for say X is a finite state space or countable state space, then S is any subset. And if I want to know the probability of transitioning from a point X to a set S, it's just Px to S, and that's defined for every X and any S in some class. So this, we replace the derivative by a difference. And then everything else is the same. And this is called Poisson's inequality. I think I came up with that name.